So somebody help me out here. Let me do this. Let's say I've got a population. Let's say that I'm investigating to see if the water somewhere has too much particulates, too much pollution or something, right? You with me? So I'm going to take samples. So I take 50 samples, and I'll look at the average number of some type of particulate. Are you guys with me? Okay. Because there's been complaints that the water tastes weird and that people are getting sick and all that kind of stuff, right? I take 50 samples and I get a sample mean number of particulates, right? What would the population look like? What would the distribution of all sample means, of all samples of size 50, what would they look like?
Normal.
Why normal?
You have 50 samples.
Yeah. Well, the sample size is 50. Sample size is 50. So all the samples, if I took every possible sample size of 50 and I plotted their averages, it would come out looking normal. It's probably the best normal curve I've ever drawn. Look at that. All right, sorry. I'm not a good artist. Can you guys take a minute? I want to know, this is going to sound very familiar. This is what I did before getting us ready for this. What is the probability that our sample is, let's see, which way do I want to do this? Yeah, what's the probability our sample is between a z of negative 1.96 and a z of 1.96?
60, no, it's one standard deviation.
So you got your z-score charts?
Oh.
Here, we'll do it together. And then I'll show you a beautiful little shortcut. This picture represents, if I was somehow able to take every possible sample size of 50 of the water, that's not even possible. But if I was, and I plotted all the averages, it would come out looking like this. So let's see. If you look at negative 1.96, what do you guys get?
0.0250.
0.025. I love it. And if you look at positive 1.96,
0.9750.
so what percentage is in here?
9750 minus 0.025.
Right. I subtract those two areas. Makes physical, visual sense, right?
Could you also just double what you got for?
Yeah, you could. There's a couple that you could say. If there's 2.5 there, there's 2.5 there, and then you can figure out what's in the middle, right? So if there's either way you do it, you get 95%. Either you do 97.5 minus 0.025, and you get 95%. Or if there's 2.5% here, what percent must be here? 2.5, because it's symmetric. Boogie woogie. So there's 5% total, so there must be 95% inside. Are you guys all with me? So that's the technical nuts and bolts of it. Here's the conceptual part of this. If we come along and we take a sample of size 50, what is the probability that it falls in here? 95% chance, right? If a lot of people, let's see, we could go out and we could take a sample of 50, correct? We could, as a group, we'll go out and we'll take a sample. What if another group does their own sample and some other group comes over and does their own sample, right? It's some weird competition. We're looking at each other like, you don't know stats, right? And we're all taking our own samples. Will we get the same sample means? If we go out and take a sample of size 50 and another group takes their own sample of size 50 and another group comes out and takes their own sample of size 50, will the sample means be the same?
Yes. No, that'd be pretty similar. At least.
You said two different things there.
Okay,
I
sorry.
really want you to understand.
My bad.
Let's take it like this. If you take a sample of 50 gross 1 students and get an average age, and you take a sample of 50, and you take a sample of 50, and you get a car, what do you think that each of your sample means will be the same? Close, sure, but would you put money on them being the same, the exact same? Hell no. Because variability. If you just pick your own sample, you have no idea what the other people picked, you picked your own sample, it is really unlikely you picked the exact same people. Right? Are you with me? Maybe. So, I don't know if you noticed, but I'm a teacher, and with my salary, I definitely, I would still put money, with my salary, I would still put money that the means would be different. I would put a lot of money down on that shit, right? I'm gonna make some money. Okay, maybe.
That's unfair though, you're the stats guy.
Huh?
You're the stats guy.
I'm the stats guy?
Yeah, so you have an advantage. Put money on.
Sure, man. It's good to know shit. Okay. So what percentage, if a bunch of different groups go out and take samples, what percentage of their means will fall in here? You can do it. If a bunch of different groups went out and took a sample, what percentage of those sample means will fall in here? 95 freaking percent. That's what that means. What percent of the time will a group get a sample whose sample mean is not in here? 5% of the time. I love it. Okay. There is no way in hell that we could actually construct this picture, like physically, go out. Because what would it take to construct this picture? And I know I just drew it, but I mean, really, I would have to take every possible sample size of 50. So what do we do instead? So let's say that we go and take a sample, and we get a sample mean of, I don't know, 50 parts per million. Or so we get a sample mean of 50. That does not communicate enough information. If another group goes out and gets a sample mean of 42, and another group goes out and they get a sample mean of 57, it's not good enough to just, and we already know this, just telling me what the center is not good enough. So a way that we've developed to kind of communicate better our confidence in what we see, right? So is to develop what's called a confidence interval. So there is a actual true mean here, right? There's a real mean. And what are we trying to do when we take a sample and find a sample mean? What are we trying to do? What is it we're actually trying to do when I go take a sample? What am I actually trying to do? If I didn't know,
Trying to find the mean.
trying to find what?
The mean.
Which mean?
The mean of
The real mean. I'm trying to find this, correct?
Yeah.
Can I ever actually get this?
No.
In this case, especially. There's no way in hell you could test all the water. I mean, every drop of it. There's no way. So when we take a sample, we're doing our best to approximate what the real mean is. Does that make sense? Of course it, that's what we're trying to do. We're trying to figure out what the real mean is, trying to get a feel for what that is. So if I just say this, that gives a false sense of confidence that it's 50. I would rather say it's 50, give or take something. Plus or minus 3, plus or minus something, right? Does that make sense? So if you said, how many people do you think standing over there? And somebody said 78, you're like, what are you Rain Man? What the shit? But you could say like 70, give or take 20, right? Let me make sure you guys really get what I'm saying. You see a group of people standing over there, and somebody's like, how many people do you think's over there? You could say, I think it's 100, right? But if somebody really pressed you, you could say like, give or take 20 people, I don't know. If somebody else said 100, give or take 5, that other guy seems to have it locked in better, right? At least that's what he's communicating to. Okay. So, let me kind of focus on a piece of this. So all three of us, all three groups are trying to get a feel for what that is. We're all trying to get a feel for what the real mean is. So every time a group comes out and takes a sample, they're going to get something. It's really unlikely that the sample mean will actually equal the real mean. but it should be close, correct? So they come out and they take a sample, some other group comes out, say that's X bar 1. Say, yeah, those are very different, Jeff. Darn it. Oh, well. How many colors I have? Very few, okay. Another group comes out and they get a sample, and another group comes out. They're gonna be orange, and they get a sample. Okay. What we do is we do this. 95% of the time, any sample taken is gonna fall in here, correct? So at worst, 5% of the time it would fall over here, for example, or over there, somewhere outside of there. So what we do is let me see if this, really, so let's say that I take a sample and I get right there. If I go down 1.96 standard deviations and up 1.96 standard deviations, in this case, do I catch the real mean?
Yes.
Yes, because I'm within here. So that X bar is less than 1.96 standard deviations away, correct? This is all weird shit, but I want you to. So if another group came along, so that would be these guys, right? I should have done it in brown. Too bad. It's too late. Let's say the orange guys. The orange guys, well, they're right there. So if they make this interval, they definitely catch the real mean, correct? I should have made the blue lower, but too bad. So then let's say the blue, let's say they're down here. If they make a confidence interval, they're not going to catch the real mean. What percentage of the time will a sample lead to an interval that catches the real mean? 95%. 95% of the time, your sample mean will fall in here, which means if I construct this interval where I go down 1.96 standard deviations, up 1.96 standard deviations, 95% of the time, I'm going to catch the real mean. So, that's the idea behind this. All we're doing is trying to come up with a way to communicate to people what we think the real mean, where we think it is. So it makes more sense if somebody, what do you think the average is, 70? Well, it makes more sense if I said, okay, what do you think the average grade's gonna be? And I say somewhere between 60 and 80. Or if I say somewhere between 70 and 73. Doesn't that communicate different states of being confident in something? Okay. All right, so let's rein this in. This is all concept up here. So let's talk about the specifics. How the shit do we actually do this? Okay. So go back. If I take a sample of 50, what happens to the standard deviation of the sample means? What happens?
It's for a sample
Yeah,
set.
so the standard deviation of the sample means?
It's over the square root of 50.
Yeah, in this case, square root of 50, 11, right? Okay. So if I want, let me see, I better draw this a different way. So if I want to go, so I take my sample mean, and I want to go 2 steps up, 1.96 steps up and 1.96 steps down. If I do that, I'll be 95% confident that I catch the real mean, based on what we said earlier. There's only 5% of the time that my sample mean will be too far away from the real mean. Does that make a little bit of sense? Okay. This is one of the weirdest things to get, by the way. It really is, but it's not that bad. 5% of the time, our sample mean is going to be too far away from the real mean. So when I construct this, it won't actually catch it. So 95% of the frickin' time when we construct this interval, we're going to catch the real mean. That means we're 95% that the interval we make catches the real mean. So then we can be very honest. We're not sure, but we're 95% sure. I mean, that's That's why I love statistics. It's so honest. Math is like X is 3. You know, statistics, you know, which is what's real life like. Yes? You guys live life? Okay. Sorry. So, what does this mean? Remember this formula here?
Right, that's
It's like the definition of z-score, really. It's the number of standard deviations away from the mean to a data point. So if I want to know what these actually are, I want to actually know what these are. How many parts per million are these? I'm actually going to construct something based on this. Do we know what the actual mean is?
No.
So we use the next best thing. That's our best guess. I want to go up and down. So I'm going to put a plus or a minus in my formula. Don't I want to go up and down so many steps? This many steps. And then what happens to this? How did I get X bar? I had to take a sample, and of course when I take a sample, the standard deviation of the means becomes X. This is the formula to construct a confidence interval. This is it. This is the formula. We're going to learn 3 of these things. So this is our first one.
So this is how they come up with that, like, oh.
Yes.
Okay.
The second thing we're going to learn, is based on percentages. So do any of you pay any attention, or actually I'm going to just ask this question and then I'll follow up. Any of you guys pay any attention to stuff like politics, the election stuff? Anybody not want to but still can't escape it sometimes?
As much as I have to.
Have you ever heard something like this? 40% of people are going to vote for Bob. 42% are going to vote for Sarah. And then at the bottom it says plus or minus 4%. Have anybody seen something like that? So, do you think that there's some guy in the room next door, Tim, he says, hey, let's cover our ass, put plus or minus 4%, we don't freaking know. No, this number, what do you think would make this number, all right, let me make sure everybody understands. So this means they really think 36 to 44% are going to vote for Bob, and 38 to 46 are going to vote for Sarah. You guys see what I'm saying? So right now, from this, doesn't it look like Sarah's in the lead? Could Bob actually be in the lead? Because again, Bob goes from 36 to 44. Sarah goes from 38 to 46. So Sarah could actually be 38. Bob could be 44. So if you see a poll, good Lord, Jeff, how many puberties are you going to have? If you see a poll and you see, 48% going for this person, and you see the number and you're like, why would I even vote or something? Holy shit. There's a built-in, what was that based off of? A sample, right? And they have ways. One of the immediate things the student thinks of when I say what could happen is, and it makes sense, you would say, well, somebody could lie. If you construct a poll well, you can actually control for lying to a certain degree. But you can't control for it 100%. So that's a valid point, but still, that doesn't happen often enough to throw things off. Another thing is, how big was your sample taken? So let me ask you again. Well, I haven't asked you yet. How would I make that number go down?
Bigger sample.
A bigger sample. The bigger the sample I take, the more sure I should be about what I see in the sample. Yeah, I like it. What kind of sample should it be, though?
Random.
It's got to be random. Now I could do stratified, I could do cluster, blah, blah, but it's got to be a random sample for me to really trust it. Okay. So if I sample my friends and I'm like, it looks like Bob's going to win, it's like, it's your friends, man. No. Y'all think the same, probably. Okay. I'm still doing concept. Let's do an actual problem, and then I'll show you a real life example of this shit. Okay. All right. We're about to get into I can immediately show you statistical analysis and show you this happening. Do you understand what I'm saying? We could have done that to some degree, but now the next few chapters are going to immediately relate to statistical analyses conclusions and the work that they do. So you'll be able to interpret them better. So whenever you see a news story, this is what kills me. If you see a news story and it talks about a study, If it doesn't have a link to the study, screw that news story. Find a link to the study. Look at it, right? Because depending on what source that is, they could spin that sucker all kinds of ways. You go to the source. Okay, maybe. I'll get some converts. Okay. So. This here. Let's do this. So let's say we take a sample. 82 Grossmont students. And find an average age of 25. Now here's the part that's going to sound a little weird. The standard deviation of the population is known to be what do you got, Jeff? Let's do it. 11.19. I like it. Find the 95% confidence interval. CI is affectionately confidence interval for the true mean age. Now I'm going to say true a lot just because it's stuck in my head, because that's what my teacher taught us when I learned this way back when. What should really be here is for the population mean age. So when I say true, I mean population, the whole group. So we take a sample, we find this. What's the likelihood that that's the actual average age of Grossmont students?
95%.
No. Very low chance.
Oh.
Right? It could be close, but I would put money on this not being the actual average age. Because this comes from a sample, correct? And samples have natural variability. It's almost always going to be different. So somebody help me out. What's the Z-score for this? We already figured that out a minute ago. 1.96. And let me show you something on your...
Just 'cause it's normal, right?
Maybe I'll show this in a minute. Yeah, I'll leave this set up alone. I'll show you something real quick, but we already know that. And what's the X bar? What is it? Sorry? 25. X bar is 25. What's sigma?
11.19.
11.19. And Z is 1.96. The plus or minus is built in, right? I want to go up and down so many steps. Okay, maybe. So now if I just plug stuff in, the mean, give or take, 1.96 of these. What was N, by the way?
82.
82. So what I would calculate first, let me see if you guys understand. Does this make sense? This is our best guess. Do you guys agree? In fact, the book is going to call this the point estimate, because the book is weird. I just call it our best guess. So our best guess for the actual average age of all Grossmont students will be the mean we found. Of course, that's our best guess. That's the only thing we know. This part, this is 25, give or take so many years. So does it make sense? We actually call this part, bless you. We don't call it bless you, we call it the error. That's how much we think we're off by.
Margin of error.
Margin of error. I love it.
I the whole news thing, I genuinely believe they were just making it up.
The what now?
With the news.
Oh, sure, yeah. No, it sounds like somebody's going, hey, we should really say give or take 4%. Okay. But the bigger the sample they take, it should become 2%. Yeah. And now you can see what happens to the error when n gets bigger. What happens when I divide by a bigger number? It gets smaller and smaller. So the bigger the sample, the smaller my error, which only makes sense. Day one, we knew a bigger sample was better.
I was gonna say, if you add 25 plus 1.96 over that
Well, first get the error for me. That's my big clue, is to do this part first. I think it's 2.2. I don't know what I'm talking about, though. That's the problem.
2.422.
That's about too bad. 2.422? So now you do, and I love it, I did have one semester a student ask me where the plus or minus button was in the calculator. And I just had to, my knees got weak. So what's, do you do 25 minus that, 25 plus that? So somebody help me out. I can do the plus. I can do the minus too, but let's see. I think that's what it is. Is that true?
Plus was 27.42203 and minus was 22.57797.
Kick ass. Okay, let me stop for a minute. This is much more informative than somebody just saying, yeah, I think the average is 25. It's much more informative for somebody to tell me, yeah, I think the average is somewhere between 22 and 27, blah, 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 right? If somebody else came along and said, I think the average is somewhere between 11 and 50, you're like, what? Get out of here. That's not very helpful, is it? That would tell me they should have taken a bigger sample, right? Let me stop for a minute. I want to make sure. The nuts and bolts of actually calculating this, stupid easy, right? They have to tell me the average. They have to tell me the standard deviation. They have to tell me the sample size. The one thing that could change is how confident they want us to be. So we'll talk about that in a minute. This problem is not done. This is the answer, correct?
I think so.
Yes, that's the answer. Here's why the problem's not done. You guys are gonna love this. When you hear me say that, you're like, okay. You have to write a conclusion. You have to write, tell me what the hell that means. It's just somebody who feels confident enough to tell me what they think that answer means.
Right, conclusion.
What do you think this answer, what do you think this means?
That,
Based on what we were talking about earlier.
That we're looking for the true mean age is somewhere between 22, 27, the decimal, right? So, because the question is asking for the true mean age, right?
Sure, yes, okay. All right, so part of your answer should include the true mean age somehow interacting with this interval.
So, like, we are 95.
Good, okay, there's the beginning. We are farmers, no, we are 95% confident.
That the true mean age is between 22.
Almost.
Ah, damn.
Remember, the whole, this is where it gets a little weird. The 95% is if I had a lot of people making an interval, a confidence interval. 95% of those intervals would catch the real mean. That's the very first thing we talked about. You guys with me? We saw a visual on why that was true. So if 100 people make confidence intervals, I would expect 95 of them, bless you, to catch the real mean. So we're 95%. So we are 95% confident that our interval, that the interval, 22.578 years to 27.422 years, contains or catches, I like to say contains, the true mean age of Gross Point students. Of G students. So you guys can see that. So whenever you make a confidence interval, you're going to say, we are so much confident that this interval, blah, 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 contains the true whatever. Right? We are this confident that our interval contains the true fill in the blank. Maybe. Hopefully that makes a little bit of sense based on the conceptual thing we did at first. Because, so again, there's a real mean that exists somewhere. We're trying to catch it. So we can't say I'm 95% sure that the mean falls in, because the mean doesn't fall anywhere. It's sitting there. The mean doesn't move around. It's just sitting there. So we're 95% sure that our interval catches it. So the example I like to give, even though I don't like to eat seafood, anybody here with me? Anybody here not like seafood?
I don't like sushi because it's weird.
All right, so all you guys can have my seafood. But I like this example. If you wanted to catch a certain fish in a pond, right, and you throw out a net that catches 95% of the fish, how confident are you that you caught the specific fish you wanted? 95% confident. So if I throw a net that catches 95% of the data, I'm going to be 95% confident that I caught a specific data point, being the actual mean. Maybe. If I made a 90% confidence interval, do you think it would be narrower or wider than this one? If I made a 90%.
It'd be narrower.
Narrower or wider?
Narrower.
Narrower. If you make a 90% confidence interval, how much data do you have to catch?
90%.
Less. So of course it would be narrower. Are you guys with me?
It's a little weird to think because, like, you would think
I know.
less confident you'd have a bigger
Yeah,
range, right?
but that's sort of like, if somebody said, how old do you think they are? And you're like, 25 to 30. I'm 50% sure that they're 25 to 30. How useful is that 25 to 30? Is that very useful? No, that sucks. So you got a nice 25 to 30, that's a good interval, right? But you're 50% sure. So I'd much rather have somebody go, there's 20 to 35 and I'm 98% sure about that. All right, 20 to 35 is a big interval, but they're 98% sure that they're in there, right? That's a little more useful, maybe. Okay, a lot of I know. So the most, I don't want to say that. There will be a few conceptual questions, but the biggest conceptual part of these problems will just be writing this. The rest of it will just be the nuts and bolts. So, let's do this. Yeah, let me show you this like I said I would. Because I don't think I have yet, right? No. This one. Okay, sorry there, buddy. There you go. So, do you guys know anything about gas stoves? Are they in the news? Gas stoves?
Yeah.
They're in the news a little bit. Yeah.
A little too much.
Evil people try to take my gas stove. Whatever. Shut up. There have been studies that have shown links between gas stoves and asthma in children, for example. Those are actual studies. Now, all of us in our daily lives take on a certain amount of risk, right? So that's where the discussion can be had, is how much risk should we allow people to take? So for example, are there seatbelt laws?
Yes.
Yes. Do some people feel like, gosh, that should be me, man, I'm a gambler, I shouldn't have to wear a damn seatbelt? Sure, but there's a law because we're like, we want to try to save your dumb ass. Yes.
I actually saw like a video compilation of people like back then reacting to when drunk driving became illegal.
Oh, yeah.
Like the DUI, and they're like, man, it's like, what's wrong with just having just a beer on the way to get your kid? You know?
Exactly.
Like,
Exactly.
What are we, communist Russia?
Exactly.
It's like, damn. You know,
Yeah.
this is against this drunk driving.
There's a good point you're bringing up, because there's a lot of discussion now about other things, but then you look back, for example, when the phone was even when the radio was invented, people were saying, oh my God, nobody's gonna do anything, they're all just gonna sit around listening to the radio. Whoa. And then every time we've had a new invention, it's been the same thing. Or anyway, so it's interesting to go back in history and see what people were saying about when they invented the phone and seatbelts. Seatbelts, there's a lot of pushback about seatbelts. Okay, so I want to show you, I'm not going to go through this whole thing. You can look up, you can Google search, I just Google searched gas stove study. Right, so you can do that if you want to. This is just one that I happened to find really quickly. And what I want to show you, most importantly, they talk about all the different gases and such, but I want to take you down to, ooh, look at that. Ooh, that, oh, dude, look at that. Oh, sorry, we're not going to talk about that weird-ass thing. I want to show you right here. Let me zoom in on that. Ooh. You remember how to do that. Holy shit, Jeff. Where'd he go? 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 I'm good at this. Let's see. Hold on. Here it is. Okay. There we go. What do you think that means?
That's a 95% confidence.
95% confidence interval. 3.3 to 9.7. All right. So it's a standard way of communicating what they. It's an example of, this is descriptive statistics. That's sort of inferential, but not really. This is describing. This is a better way to describe what we found. So they found a mean of 5.8, whatever the hell this whole mean benzene emission rates, blah, blah, blah. 5.8 from ovens set to 350, gas burners on high, and from oven, okay, I see. So it was 2.8 for gas. It doesn't matter. What matters right now is they constructed a 95% confidence. Almost any study you look at, it's going to provide the data they saw, it's going to give a confidence interval for it. And this is informative. When you know more statistics, you want to see that kind of thing. It gives you an immediate feel for, well, how sure were they about what they saw, right? 1.7 to 4.6, that's not that bad. It's pretty good. That's pretty good. They had a pretty good feel of what's going on. If it was 0.1 to 12, I'd be like, oh, okay, it's not that great, guys. Okay, maybe. The immediate reason why I want to show you this is I really know this in algebra. When I would teach that, and a student would look at me and say, "When the hell am I going to know how to solve for it?" Oh, God, help me. Here, you're seeing the work you're doing. Somebody who is paid to do statistical analysis is doing the exact same damn work. It's right there. It's right there. All right, I'll stop. Sorry. So, the most commonly used confidence interval is 95%. And the reason that is they want to kind of standardize it a bit, because somebody somewhere could just do an 80% confidence interval and hope that they can sneak it past people, right? You guys with me? So if you do a lower confidence interval, you can actually make your confidence interval look better. So that's why they're trying to standardize it at 95 so that you can compare amongst all these different things. There are valid reasons to use different. So what up here exactly would change if I wanted to be 90% confident instead of 95? What's the immediate thing that would change?
Your
Z-score. Right? Because this came from, the Z-score will always come from how confident we want to be. And why does that make sense? Because the Z-score tells me how far to go out to catch a certain percentage. So if I want to catch less, I'm going to go out less. Right? So can you guys figure out, don't say anything. You got your Z-score charts? Figure out what a 90%, what the Z-score would be for 90%. Yes, right. Now I want to show us. Got too much shit up here. Okay. So 90%. What percentage is in that tail there? If there's 90% inside, how much is outside? So how much is on that side? So if I look up 0.05, hey Calvin, if I look up 0.05, what do I see? Oh, look at that. Do you guys see that? The closest I can get to 0.05 is right in between those two, and that would be negative 1.645. So what's that? 1.645. I love it. Okay. But is it on this side? No. If you look on the other side real quick, this is what I call the baby chart. You'll see the, oh, look at that. Do you see confidence interval? 90% confidence level. Z-score is 1.645. These are the three most commonly used confidence intervals. And they just tell you what the Z-scores are, right? Now, you know, you've met me. You know on a test, I'm going to ask you to make a 96% confidence interval. Is that here? Damn it, you're going to have to do it that way, right? You don't need this. This is just a shortcut. We know how to do it otherwise. So that's me, again, telling you what is going to happen on the next test. Okay. So if we did all this work again, but instead of 1.96, we put 1.645, of course the error is going to be smaller, correct? It's going to go out less. I'm going to catch less data. I'm going to make my interval tighter, but at the expense of being less confident. Now, a really good question that I haven't heard yet. How do you become 100% confident? You go from negative infinity to infinity, then you're 100% confident, right? It's like saying, how long do you think it's going to take? Oh, somewhere between 0 hours and the rest of time, I think. Oh, that's useful, thank you, right? Paying you by the hour. Chop, chop, okay. Maybe? And that part doesn't matter that much, but it just, I'm curious if that was boiling somebody's brain was like, how do you get 100% freaking confident? I love statistics. Statistics look at you and go, just take everything. All right. So let me give you this. You're not going to believe this, but I have a handout. So the side that talks about dolphins. Side we're going to look at to begin with. And this row is gone. Thank you. So.
Professor?
Yeah.
So I'm just kind of like in here. How do we get the Z-score for the 90%, for the negative one?
90% inside, 10%. So there's 5% over there. So if you look up 0.05 and
Okay.
look out, you get a
Oh,
negative
okay, so
1.645.
you get that. Okay, thank you.
And here's the thing, that negative, I'm not gonna, it's the plus and minus is built in, correct? So I really am just curious about what that number is. It's 1.645, and then I can plug that in. The negative's already built in. People get confused about that. So I want you guys to try this one out. 1A. Time is it? Yeah, we'll probably take a break after this. Million, 92.6, give or take 1.96 of these standard deviations. 4.11 divided by square root of 37. What did you guys get for the error? 1.324? Okay, so in this case, rule of thumb, I would go out at least 2 places, right? Okay, I like it. When I say at least, by the way, don't give me 8 decimal places. There's no need for that. Okay. So now I just add that and subtract that. What am I going to get? You could do it, Jeff. 91.276. Really? Okay. And then 93.924. Does that sound good? Okay. Look at that. The math guy could do math. So that is technically the answer. That's the confidence interval. But obviously, beyond the numbers, the most important thing about statistics is understanding what the hell you just did. And then on top of that, that's one level. And then on top of that is the ability to communicate to other people that don't understand statistics what the hell you just did, right? That's the next level of this. All right, so let me see. Who thinks they've gotten the conclusion written correctly that I haven't heard from yet? Anybody? Yes.
We are 95% confident that the interval 91.2757 inches to 93.9243 inches added to 4 decimals contains the true mean length of all dolphins.
That's perfect. I got little tears coming out of my eyes. We're 95% confident that the interval blah 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 contains the true mean, or you could say population mean, it's up to you, true mean length of dolphins. Okay, you guys with me? Now let's say this. Let's say that we happen to know that the average length of just all dolphins is 102 inches. Have we just found evidence that there's an issue in the area that we took our sample from?
No. Yes.
Hell yeah. If there was, let me see if you guys can get this. If there was no issue, what should our confidence interval contain?
Oh.
102. Because that's the actual average. Is our confidence interval not only not contain that, but actually not go anywhere near that? Okay. So this is exploratory statistics. Is it still possible that the sample we took just happened to be shorter dolphins? And the really long dolphins are all like, go see what those, hey, you shorty, go see what those idiots want up there. Okay. Right? I don't know. Sorry. You guys kind of with me? You understand? But what's more likely is there actually is a problem, right? Because we took a nice random sample. It's probably not likely that the long ones make the short ones do shit. I don't know. You guys kind of with me? So what would the next thing be? Test the water, test the food, test the temperature, what's happening on islands nearby. You guys see what I'm saying? Now I go in full force because now I see evidence that there is something different. Okay, maybe. So a lot of the time you have this exploratory statistics first step. This was relatively quick. Now actually, it was really quick because we got the data, but you go out on a boat, you kind of sample dolphins' lengths. You kind of have to do that anyway as part of your job, but now you're being specific about this area, and then the construction of this was pretty quick. Now I could do a deeper dive. Now I can do more detailed statistical analyses. Okay. Part B would just, what would the only difference be? We basically already did this, but what would the only difference be? Z-score. So now the formula would look exactly the same, except right here I would put, 1.645. And of course we already know, just theoretically it makes sense that it gets narrower because we're catching less stuff. But mathematically, I'm multiplying by a smaller number. So of course this amount gets smaller. I go up and down less. Okay, I like it. So let's do this. Let's take a break. Let's see. 10, come back at 10:25. All right, start 10:35. You're all like, you're so nice, Jeff. 10:35. Come back at 10:35.